Okay, so our next speaker is Dr. Jason Weiss, currently Edwards Distinguished Chair of Engineering at Oregon State University. I think when we met, you were at Purdue.
Yep.
At that time when I was working for NPCA and also in Indiana. So Jason is going to talk about reducing the GWP of concrete, reactivity, EPDs, and optimization. So take it away, Jason.
Awesome. Thank you. All right. And I appreciate Tom talking about the fact that we're moving people's cheese. And what I want to just mention here is as we start moving the cheese, I don't want us to lose sight of our overall goal. And I think one of the things that we tend to do is, as an industry, is we tend to focus on one specific number. We get fixated on that, and we can lose perspective on what we're trying to do. So we're going to talk about the global warming potential, but we're also going to talk about reactivity, optimization, and really where we're headed long term. And I want to just acknowledge Professor Burkhan-Isgor, who's done a lot of the work with us here, and I'd like to just start to jump into this. If we look at the Global Cement and Concrete Association roadmap, over 50% of what we're going to be doing to reduce CO2 is stuff we can do right now, right? So if you look at it, efficient design, efficient concrete production, reducing the binder, reducing the clinker, that's over 50% of what we can do doing normal standard concrete that's already scaled. Right? We can do this efficiently, we can do this currently. We don't have to come up with magic dust to do this. This is something we can do today, right now, all right, with existing codes and existing technologies if we put in a little bit of effort. Right? But what we really want to start to try to do is we want to start to try to quantify how we're making these mixtures more sustainable. And one way that this is done is through an environmental product declaration, the EPDs. And some of you will look at this and say, that's the NRMCA EPD system. All right. One of the things that I want to do is I want to just point out that NRMCA did work with Athena to establish LCA for a variety of mixtures. As this was going on, many of us said, please make sure we don't just focus on compressive strength. So what you notice is all of these categories are based on compressive strength. All right. And the big thing I would just mention is compressive strength has been related to the GWP, but compressive strength is a measure that at its best is incomplete in this discussion. And as Tom mentioned in his talk, and I think this is going to become a theme as we start talking about the move cheese, we can't just continue to focus on compressive strength. There are many other things that we need to do. The goal, and what you'll see in the 323 document that was being discussed earlier, is trying to take that global warming potential for different strength concretes and reduce it by a certain percentage, whether it's 15 or 20%. So the question is, what about this concrete mixture? All right, is it the best of times for this concrete mixture? Is it the worst of times for this concrete mixture? All right, is this a good mixture from a GWP perspective or not? And we could start to dig into this, all right, and we could start to do some of these calculations. So this is a fairly standard DOT mix. It's an NDOT Class C. It's what a lot of the Midwestern states are using. It's fairly typical, not surprisingly because it's widely used. It falls very close to the NRMCA data. You can see the little green box over there, or little purple circle over there. It's right on the line, all right? What I would mention is this is more aggressive than the typical exposure, all right? Because it's more aggressive than the typical exposure, compressive strength isn't capturing everything, right? But if you actually look at the GWP calculation there, what you'll notice is the total amount for the yard of concrete is 273 kilograms of equivalent CO2 per cubic yard, but 240 of that is coming from the cement. Right? So the first big thing, and you saw in Dean's slide a little earlier, lots of people focusing on the binder. The reason they're focusing on the binder is because it's 85 to 90% of the overall, all right, global warming potential. Right? So the question comes out, could we do something to make this more efficient? Right? And Tom talked about, his mix 2 was a slag replacement. Here we see a slag with a little bit of silica fume being added. This is a real concrete mixture. All right, it was mixed and designed before people were super excited about global warming potential. But the big thing I would tell you is this dropped the global warming potential by about 17%, very similar to what Tom saw. All right, but in doing that, we also got a very substantial increase in strength. Right, we went from around 4,000 psi to around 7,500 psi. Right, we're now at that little yellow star, all right, that's over there on that graph. So reduction in GWP, but we moved over. So again, we could ask, is it the best of times or the worst of times? Right, Dickens asked this question, right, where he had the tale of two cities. I'm going to talk about the tale of three concretes. All right, so as we look at the tale of three concretes, we're going to look at that conventional mix, the mix where we had the slag replacement, and then I want to talk about a mix with internal curing. Right? Internal curing is just replacing a portion of the sand with lightweight sand that's porous. Right? It provides curing water to the system that does exactly what we want in our concrete. It cures the cement to make a glue. Right? That's the whole purpose of this. It helps to reduce cracking in those systems. Now, if we look at this, this is our conventional mixture that's going out there, right? The one with the SCM is over there, and as Tom showed, it's incredibly important that these can be actually placed, right? These are being placed in real life, right? And as they're being placed, we're actually taking a whole bunch of data, all right, and we're looking at this. Now, one of the interesting things when we start to look at the internally cured mixture, right, and we do our tally, we find out that we had our original mix, which was the Class C mix, which had a global warming potential of 273. We dropped the global warming potential by using slag in that mixture and replacing cement with that. But we see the global warming potential go back up when we replace sand with the manufactured lightweight aggregate sand, all right, in the system, all right? So we're back up to that 277 value. And if I asked you which one of these mixtures would you choose, all right, for your project, all right, which one would most people in here want to choose? It's the class participation part.
Yellow star.
The yellow star, right? We're going to go to the yellow star because we're fixated on the global warming potential right now. Right? As an industry, we can only focus on one or two things at a time. Historically, it's been compressive strength in dollars. Now we've thrown this global warming potential thing, and we're fixated on that. And we would say that's the mixture that we want to go to. But I really want to start to ask a couple questions as we start to look at this. Is the performance actually important? When these were put in place, this is the conventional mixture. You can tell that it's got a very nice crack pointed out by that Sharpie pen, all right, that's there. So if that gives you some size scale, all right, it is a very nice crack. Where the one on the far side, all right, is that third mixture that we talked about that was crack-free, all right? Which one of these do we want? Okay. Now, if we look at the time to corrosion of these mixtures, right, and we do some diffusion calculations, not assuming there's any of these mixtures have cracked, which we already saw the plain conventional mixture did crack, which provides a superhighway. We see that the first mix starts to corrode at about 20 years. The mix with the slag, we go out to about 35 years. The mix with internal curing and slag goes out to about 60 years before we start seeing corrosion. Right? So now all of a sudden, this starts to impact our thought process because we've changed the compressive strength by taking some cement out and putting some slag in. We've also changed the RCPT values here pretty substantially, and we've done more sophisticated service life modeling where we've shown those times to corrosion. And all of a sudden now, we can start looking at this global warming potential in different ways. And one of the arguments that I'm going to make is a challenge with the way we're looking at the GWP right now is we're entirely focused on A1 to A3, cradle to gate. We are not considering the fact that the concrete is going to be out there to do something which we've designed it for. And if we start to figure in a 75-year period and we look at the equivalent kilograms of carbon dioxide, right? Didn't do all the service life modeling yet, right? But we look at these, we see a very different evaluation of these mixtures, right? If we take the global warming potential and divide by years, we see we're way down about 40% when we start to talk about that internally cured mixture, right? If we look at the bridge over this time period, right, NDOT would have replaced this bridge by about 2.5 times over that period, where the internal curing bridge, we use one bridge. Now we can have a whole discussion there, but you see, we've got about twice the amount of carbon in that over the life of the system, right? This is something we are not currently accounting for. And we've actually gone through and done some life cycle modeling with these. Now, I want to point out that this is a very interesting case because the bridges were built in Indiana. The life cycle model is actually done assuming the bridges were placed in Minnesota, all right? Because the people who did the traffic modeling had a Minnesota model, and they said, we're going to drop this in there. But they did all of these calculations over the 75-year period and started to look at the differences in what the actual costs are, not just the carbon costs, but what the costs are to the DOT as they're doing these different replacements. The first column is our normal concrete with a partial closure. Second one is our high performance concrete with a partial closure, that middle mixture. And our third one is the internally cured concrete with a partial closure. If we do the three columns on the far side, it's again the same three mixtures, but they're fully closing the bridge to replace it. And when you start to look at the present value of dollars associated with that, you're starting to get a very different picture, especially when you start to bring traffic and safety into those pictures. All right? Much, much bigger savings when we do long-lasting materials, all right? Much better overall performance. So again, if you take anything from this portion of the talk, what I really want us to do is actually start having a deeper discussion that says we have to go past A1 to A3 thinking. We have to think about the overall performance of the concrete, right? We have to design for a different performance, we have to simulate a different performance, and we have to start coming up with some way to do this a little bit better. Now, one thing I want to mention as we did this, when we just replaced some of the powder with the slag, you saw our strengths went up, we got a different service life. So one of the things that we're really trying to do now is saying, rather than just design for strength, let's design the concrete for what we really want in terms of performance, right? Our current design process, our mixture proportioning process, is not designed to give us the overall performance of every single thing that we want in the system. We have an approach where we can do this using thermodynamic modeling, where we can take the chemistries of the materials that we're working with, we can actually simulate the performance, all right, and get the overall qualities of our concrete. So we start out with the chemistry of our cement. We can put fillers in, we can put SCMs in, and what we really need to be able to do is to quantify the reactivity of the pozzolans that we're talking about. I want to be super clear when I say this. This is not a strength activity index. This is not just throwing something into a calorimeter and hoping for the best. All right, this is not doing some other crazy test that's been derived. It's a very simple test that we do to get a quantitative value of how much of that pozzolan actually reacts. We put that into a kinetic model, and we can actually predict the performance of those systems. Now, what we're saying is, the one thing I didn't mention here, and I should, every one of these properties has been validated against real measurements. So everything you're asking for, there's an AASHTO test that could actually measure that value, and we can stop and measure every single one of those as we go through the process. Now, if we started to look at this, we could actually start to design our pavements and our bridge decks differently. Instead of just designing them using the standard 12-step process, all right, that 211 or other mixture proportioning procedures give us, we could actually say, tell us what you really want that structure to do in the field, and we can optimize the mixture for that particular scenario. So here's a pavement where we want a certain strength, we want a certain formation factor, which is like the resistivity that Tom mentioned, but it accounts for the pore solution. Calcium hydroxide content, so we don't get into a problem with the icing salts, pH, so we don't have a problem with ASR, and then freeze-thaw resistance. And if you tell us all these things up front, we can actually simulate and come up with a graph like you see over on the right-hand side, which is the strength as a function of the water to binder ratio versus the SCM replacement on the y-axis. Everything that's above that solid line that's around 29, those are all mixed designs that will not give you the performance you want. Anything that's below that line and down into that corner, those are all feasible solutions. We can do the exact same thing if we start to talk about the transport properties or the formation factor. Everything to the right of that red line at 270 doesn't meet the specification. Everything to the left of the line does meet the specification. We do the exact same thing with our calcium hydroxide. And at this point, you're saying, this is fantastic. You have given me 9 graphs that I can't do anything with. All right? We can put all those graphs together. And if you overlap all those graphs together with the region of feasible mixtures, what you see is that gray blob starts to appear. That gray blob is all the mixture compositions that you could be using with a high potential for meeting your specified values. So all of a sudden now, we have a great spot to start looking for mixture solutions, right? We can all of a sudden start to say, this is the place where we would try to design our mixture. And we can go through and we can do things like the global warming potential, all right? But what we've really been trying to do is we've really been trying to say, can we do this mixture design and bring 2 things into the overall discussion? The first one is really quantifying the SCMs that you're using, right? There's lots of SCMs right now. Historically, we've had fly ash, we've had slag. We could actually be talking about ground pozzolans, we could be talking about clays, we could be talking about all kinds of new materials. We have a simple test that tells us how reactive those materials are. And I will tell you, much like my academic career, 100% is not always the best case scenario. Sometimes getting a B in the reactivity test is really what you want to be doing because you replace more of the clinker, right? If you're at 100% reactivity, you may only use 5 or 10% of the material. If you're at 50% reactivity, you're now replacing 30% of your clinker, which drops your GWP value substantially. How do we get that reactivity? We get it through science. We know that a pozzolan has to react with calcium hydroxide to be efficient. So we say, how much of the pozzolan has reacted with calcium hydroxide in a pore solution? And in doing that, how much of the calcium hydroxide has been consumed and how much heat has been generated? And once we do that, we can compare that to a scientific equation that can be written that says, when this reaction occurs, this is how much heat is given off, and this is how much calcium hydroxide is consumed, and therefore this is the percentage of your material that is reacting. Now, some of you will say, well, I could do this by getting the glassy phases and getting the crystalline phases and doing some advanced. Yes, you can, and it matches up exactly with this test number that we get doing a very simple lab test, right? And now it's not, is it reactive, is it not reactive? We don't have to go to Dick Clark and American Bandstand and get some arbitrary number. We have a percentage that's calculated based on the portion of the material that's reacting. The final thing that we're doing here is we're actually mathematically optimizing these systems. So a very simple add-on at the end of this program, all right, that we're doing is we're saying, let's take that feasible region that we had before, SCM replacement versus water to cement ratio. The one little trick I did between slide 25 and now is I switched this over to volumetric water to cement ratio because here's a little secret. Not all SCMs have the same specific gravity as cement, right? Shocking, yes. All right. Well, it's evaded our industry for the last 70 years, right? Because we've just been doing mass replacement. We should be doing volume replacements because we need the same volume of paste in our systems. But when we do this, we can actually mathematically optimize these systems. We can say there's a cost of the materials, there's an availability of the materials, and there's a cost of carbon. And we write a single equation and we say, let's come up with the cost of all those values. This blue shading gives us an indicator of the cost or the cost of the carbon, and all of a sudden we can start choosing mixtures that are optimal for what we have available. If our SCM is free, maximize the SCM. All right? If our SCMs are more expensive than the cement, we come up with different solutions, but all of a sudden now we can figure out how to use our mixtures the most efficiently. So again, I want to thank all of you for sticking around through Wednesday. All right, but one of the things I wanted to just mention is we are really great as an industry of focusing on certain things. We are focusing in on the global warming potential right now of concrete. The big thing that I'm concerned about is we are really focusing in too much on A1 to A3. We need to think about how that concrete is going to perform. Getting a really, really low GWP value for a concrete that lasts for 5 years and has to be replaced 20 times, I don't think that's in the best industry interests. Our EPDs can be great, but we need to move on past A1 to A3, all right? We need to also stop obsessing about compressive strength. Measure it, have a great time, measure it, but focus on the other things that are important. Durability, shrinkage, being able to actually place it in the field. Those are important things, all right? Life cycle analysis, all right, and I hear people say we can't do it perfectly. We may not be able to do it perfectly, but we can do it pretty well, all right? We need to start focusing on this, and if nothing else, we need to start at least estimating this into some of our calculations. And as I've mentioned, we have a tool that's designed to actually optimize mixture proportions, right? It takes the chemistry of the SCM, takes the actual amount of it that's going to react locally. We can bring in cost, and we can give you the optimal mixtures in terms of global warming potential. And with that, I'm not sure where I am on time, so I can't be as excited as Tom was that he hit his time, but I think I hit my time.
Oh, yeah.
So.
You got 10 minutes.
I got 10 minutes, okay. All right, thoughts or questions? Counterpoints?
Jason, very nice talk. And I'm glad you're finally starting to get it out to the notice that we should be looking at the total life of the structure, because certainly if I have a bridge that lasts 100 years versus one that lasts 50 years, I'm using half the carbon footprint no matter what I put in that bridge.
Right.
And I'm glad you also pointed out all those indirect costs of people sitting in traffic, and there are also it's on CO2, and also has people also has a dollar cost to this. I think that's almost as important as the science part of what we do.
Yeah, and I think, when we start having these discussions, so thank you, Neil. So, Neil's, basically, coming back and, saying a lot of these things are really important. When we look at, for example, these costs, it's amazing when we consider the cost of these bridges from a DOT perspective, right? What I want to point out is this little blue bar down here is the actual cost of building the bridge. This red bar is the inspections, and the green bar is the cost associated with patching. When we look at purple, I don't know what that other color is. I probably should be better at other blue is what I'm going to call it, because I have a very limited, I only had 8 crayons as a kid. I didn't have the 64 set, right? So other blue and orange, those are DOT costs, right? Safety, operations, travel time, right? When we start looking at those, they dwarf the thing that we obsess about, right? They dwarf that number. So I think one of the other things we need to start conveying as an industry is there are a lot of other costs that go into this system, and it's not simply the lowest cost when you buy something. Derek.
Jason, thank you for imagining a much bigger picture. We're seeing in Europe a carbon tax directly on tons of cement, which is another cost. Can you tell us how you'd imagine incorporating that into the model?
Yeah, so this is actually where we bring this into the model. We bring carbon into our optimization as a dollar amount, right? So if you said this is the dollars per carbon, right? A few years ago, Obama said it was $47 per ton of carbon, right? We bring that directly into this system, right? That's exactly how we bring it in. If it was a tax, we bring that in. If it's an imagined cost, we bring that in. And the challenge there, and the reason we went through this kind of exercise in optimizing, we had one presidential regime that said it was $3 a ton for carbon. We've had other ones who said it's $200 a ton for carbon. And we can now play those what-if scenarios mathematically with this approach to see where we need to start to end up. But yeah, and just see where does it start to make sense, right?
I need
need to use a microphone for it. I lost my voice at Christmas time. Excellent talk. I just want to make a comment. We heard in the first lecture, Dean's lecture, that we have already reached 1.5 degrees heating. So I think it is very urgent to make the concrete as sustainable as possible. And that's maybe it is more important to look at A1 to A3 despite of that. And also we have a trend that we are making better and better, greener and greener cement, greener concrete. So if we are using a rather poor product, which could be used for 100 years, perhaps we should consider to making use a little bit less concrete now in order to use the better concrete that will be available some years from now. In Sweden, we will have CCS in 2030, and if we are not overusing concrete until then we will. I think we will have a better possibility to reach our climate goals.
Yeah, so that's great, and I hope you got a really good present at Christmas when you lost your voice. Sorry, you're just screaming for something really good.
That was COVID.
Oh, okay. Sorry about that. I was hoping it was a good present, like a tricycle or something, exciting. They got everybody. No, I think there's a couple things in there that are really important. So one of these is, we can wait for the magic bullet, right? That's a great solution down the road. That may come, it may not come, right? We are still building things on our way there, right? The time value of carbon is a very important part of this discussion, right? And just like we deal with time value of money, we can also deal with the time value of carbon. So if we can reduce the carbon now, we can actually account for that. And there's a technical term, and I forget the name of it. I've put it into things I understand, time value of carbon, where it's more effective to take carbon out of the atmosphere early in the process than later. But what you notice is that's about a 15% difference over the 75-year cycle that we're dealing with here. So it's really important, though, that I think we really look at this, because right now we're so obsessed with this that, again, we might have a magic solution in 15 years that really reduces this, but I'm not necessarily as confident we're going to have that solution. And what I'm really afraid of is we've already seen some sustainable solutions go into service that after 2 or 3 years are being replaced, and that is not what I think anybody in this room wants. All right, but those are great points. Thank you.
Jason, great talk. You did all the comparison for normal concrete and HPC. Have you ever considered UHPC? How's that affect?
Yeah, so I haven't done the calculations for UHPC, but the framework that we've set up here can be extended very straightforward to a UHPC type of approach. All right, I'm not an ultra guy yet. I stretch myself to get to high performance, right? It's going to take me longer to get to ultra high, right? Okay. Other questions? Neil?
Yeah, that's applies to buildings too, I would think. And also, I took a course many years ago on building design, and they initially put a carbon footprint place, nothing compared to the operating cost of that building over time.
Yeah, so Neil's comment, for those of you who couldn't hear in the back, his comment is related to the operational costs of a building. And I mean, I teach another course on building envelopes, and I just want to point out that over 90% of the building's carbon footprint is operations, right? So we spend an enormous amount of time worrying about the global warming potential of the mixture when it goes in, and we should, all right? But it's also maybe more important for us to be looking at the refrigeration cycle or what our air conditioners are set at, because in many of these cases, our buildings have outlasted what we ever expected, right? They get reused, they get reevaluated. So I'll go there. Okay. All right. Again, thank you all.